This is part 1 of section 5.4 dealing with exponential functions. Now, we've already kind of covered exponential functions. I introduced them at the very beginning, so you should be pretty comfortable with this section. It should be relatively smooth. And we'll just kind of go over what the exponential function derivative and integral rules are. There's only 2 rules, and we've already seen them. We've already worked extensively with the derivative one, but we'll kind of focus on, for part 2 and beyond, the integral one. So we'll revisit a couple of problems we haven't seen in a while. The first one being writing a tangent line equation. So by now you should know that the reason, or the first thing you do is you find the derivative. The reason being that's going to get you the slope. So I want to find the derivative of this. So g prime is going to get me my slope. And so this first part requires the product rule. So it's going to be x e to the x plus e to the x times 1. So this is f. This is g prime plus g, and this is f prime. The derivative of x is 1. Minus, now the derivative of e to the negative x is itself e to the negative x, but then the derivative of the derivative of negative x is negative 1. So this is like the chain rule. The u prime is the chain rule on e to the negative x. Okay. So simplifying this is going to be g prime equal to x e to the x plus e to the x. These two negatives, when I'm multiplying, become positive. I'm going to write this as 1 over e to the x. So e to the negative x is the same thing as 1 over x. Alright, so when I plug in 1, that's going to give me my slope. So it's going to be, well, 1 plugged into here is just going to be e to the x, or e to the first power, I should say, plus, this is e to the first power plus 1 over e to the first power. And simplifying these, I have 2e, so this becomes 2e plus 1 over e. And this bizarre looking expression, that's going to be my slope. So this represents my tangent line slope. Alright. Now the next thing, because I want to ultimately write my tangent line equation as y equal to mx plus b, is I need to know the y coordinate. So to find the y coordinate, I plug the x coordinate back into the given function, back into g. So g of 1 is going to be, well, 1 plugged into here is 1 e to the first power, so just e, and then minus e to the negative 1. So my y coordinate is e minus 1 over e. So a whole bunch of e's and a whole bunch of 1 over e's for my slope and for my y coordinate. Alright, so the next thing is I need to plug it into the slope-intercept form to find my b, my y-intercept. So this is the y-coordinate. I'll abbreviate that. So it's going to be e minus 1 over e equal to, now I'm going to use the slope, which I found as 2e plus 1 over e. I'm going to multiply that by the x-coordinate. Luckily, I'm multiplying it by 1, so it stays the same. And I'm solving for b, I'm solving for this y-intercept. So what I can start doing to simplify this is I'm going to subtract, to isolate b, I'm going to subtract this 2e over and subtract it 2e, and subtract this 1 over e. So that reduces, or that cancels off. So e minus 2e gives me negative e, and I have negative e, and negative e gives me negative 2 over e. And this is my y-intercept. This is my last bit of the equation. So my tangent line is going to be y equal to the slope, which is 2 over e plus 1 over e, and then plus my y-intercept, which I added, which I found, so it's going to be minus e minus 2 over e. And I'm multiplying all this by x. I forgot the x variable right there. So this bizarre looking expression is what my slope is, all of this times x, and then my y-intercept, which is all of this. And really I should put all this in parentheses, and I'm all out of whiteout, so I'll have to rewrite this as 2e plus 1 over e times x minus e minus 2 over e. So since I'm all out of whiteout, and I'm going to erase all this, and this is how the answer should be written. And that looks horrendous, but I'm all out of whiteout, like I said, so that's what the answer is. Moving on. Alright. Example 2 is finding the derivative implicitly to this bizarre looking expression. So a bunch of stuff going on here, so let's just go ahead and bust through it. First thing is I find the derivative of each piece, so the derivative with respect to x of y to the 5th plus x squared y to the 3rd equal to the derivative with respect to x of 1 plus x e to the y to the 2nd. Alrighty, so this piece is straightforward. I just find the derivative of this, so it's going to be 5 y to the 4th. It's going to be implicit because the variables are not the same, so times dy dx plus. This now requires the product rule, x squared y to the 3rd. So it's going to be the product rule on that's going to be x to the 2nd times 3 y squared dy dx plus y to the 3rd times 2x. So all this is the product rule on that, and then equal to the derivative of 1 is going to be a 0. Now this also requires a product rule, so the product rule on this is going to be keep x the same. The derivative of e is itself e y squared, but now the derivative of y squared is 2y dy dx plus, and the last half of the product rule is keep this the same, so e y squared, and then the derivative of x is times 1. Alright, so we've got a whole bunch of stuff going on, so let me just kind of simplify this. This becomes 5 y to the 4th dy dx. I'm going to put this 3 in front, so it's 3x squared y squared dy dx plus 2x y to the 3rd. And this becomes, I'm multiplying 2y times all of this, so it's going to be 2x y e y to the 2nd dy dx plus e to the y to the 2nd. Now the general idea is that you want to get all the dy dx terms on one side. So I'm going to take all of this and then move it over, and then take this piece and then move it over here. So when I factor that out, it's dy dx, and it's going to be 5 y to the 4th plus 3 x squared y squared. Moving all of this over, it becomes negative, so 2x y ey squared. This over here on this side stays positive, so it's e y squared. When I move this onto the other side, it becomes negative, so minus 2x y to the 3rd. And then the last piece is just take all of this and then divide it over. So my answer, dy dx, is equal to e y to the 2nd minus 2 x y to the 3rd all over this expression. 5y to the 4th, 3x squared, y squared minus 2xy e to the y squared. And I have to extend my fraction bar, and that is my derivative answer. Alright. So, last example. It gives us the first derivative, and it tells us that it's going to have a function passing through of a certain point, and it also wants to find us the value of the function at a different point. So, in order to find this specific function, I have to integrate. So I'm going to integrate f prime. So I'm going to integrate 4 over x with respect to x. So, antiderivative, this is just a constant, so I can just take this 4 out, and then what I would be left over is with the integral of 1 over x dx. Antiderivative of 1 over x is ln plus c. Now, they give us that the square root of e plugged into the function is equal to 3. So we're going to use this information to find the c value. So think of this as your x value, this as your y value, and you're going to use it to solve for c. So it's going to be a 3. So f of square root of e is 4 ln absolute value square root of e plus c. All that's going to equal 3. Well, think of this as a 4 ln of e to the 1/2 power plus c. There's a property that said that if you have an ln and an exponent, you can drop it out in front. So this is the same thing as 4 times 1/2 times ln of e plus c. So I'm simplifying this as much as I can, and then this becomes 2. So 3 is equal to 2. ln and e cancel each other off, so I'm just multiplying this really by 1. This is going to be plus c. So really, when I solve for c, c is going to equal 1. So now that I have my function for ln of absolute value of x plus 1, which is my c value, they wanted us initially to plug in 3. So now it's just going to be f of 3. Sorry, f of e. Excuse me, I got my e's and my 3's confused. They wanted us to plug in e into our function, so it's going to be 4 ln of e plus 1, which is basically saying 4 times 1 plus 1, which is equal to 5. Alright, so that's it for part 1, and sorry it was a little lengthy. The second example took up more time than I anticipated because implicit derivatives do that, but we are finished.